Hi, ladies and gentlemen. My name is Professor Dr. Hakan from Gazi University, the Department of Metallurgical and Materials Engineering. Ankara, the capital of Turkey. Today's lecture is about the computational materials engineering and nanotechnology. I mean that the transformative impact of the digital age on material science. I'll try to deliver my keynote speech for you. First of all, I would like to best wishes and salam to all participants and the people there. My content is here, abstract definition, and definition of my materials, applications area, especially today concentrated on the computational material science and engineering, and I'll try to give you challenge and future directions, especially nanowires and computational material science and engineering. As I mentioned earlier, my presentation explores the fascinating role of zinc oxide and zinc sulfide nanowires, critical components in advanced nanotechnology. These materials are not only abundant and stable, but also environmentally benign, making them ideal for the sustainable innovation. My selection is very important, especially when we are looking at the advantage of nanoscale materials and some unique properties of my materials, especially wide bandgap semiconductors and computational age. Nanowires with their one-dimensional morphology and high aspect ratio present a unique class of the nanomaterials. Their reduced dimensionally leads to quantum confinement effects, significantly altering their electronics, optical, and mechanical properties compared to the bulk materials. This nanoscale control over material properties is what makes them so compelling for advanced application. Specifically, their large surface to volume ratio makes them excellent candidates for the sensing application, where surface interactions are paramount. The ability to project their synthesis parameters enable the tailored properties, opening up the multitude of functional devices. When we focus on the zinc oxide, their unique properties, such as piezoelectric semiconducting and biocompatible properties, make zinc oxide nanowires exceptionally versatile. Aside from this, gas sensors, one of their application area, high sensitivity and rapid response due to large surface area and oxygen vacancy defects. On the other hand, the energy harvesting side, the piezoelectric nature allows them to generate electricity from mechanical stress, leading to self-powered devices. Their structural properties like hexagonal vertex crystal structure, lattice parameters, and high thermal stability, and electronic properties like direct wide band gap, high electron mobility, strong exciting binding energy, and also their optical properties like strong UV emission, visible emission due to the defects, wave-guiding capabilities make zinc oxide very preferable materials. Similarly, zinc oxide, zinc sulfide is another important semiconductor materials. Their properties has been given the slide, luminescence, band gap, bioimaging, especially can be functional as fluorescent labels for tracking biological properties within cells, process within cells. Again, related to properties of zinc sulfide, I have to mention their structural properties. This time, their structural properties little bit different, but very important. Again, electronic properties and optical properties. The nanowire application area can be explained piezoelectric, harvesting the energy, gas sensors, and UV photodetectors can be mentioned as important or very important application areas. Computational materials engineering, on the other hand, has accelerated the development of this application by enabling the prediction of performance metrics and guiding experimental design for optimal device configuration. In this slide, I try to give comparative analysis, zinc oxide versus zinc sulfide nanowires. I try to make a table, band gap, exciting, binding energy, primary application areas, and crystal structure. While both are wide band gaps in semiconductors, their inherent properties and synthesis capabilities lead to distinct application landscape. Zinc oxide excels in sensing and energy harvesting, while zinc sulfide shines in displays and quantum technologies. On the other hand, I want to mention hybrid nanowire system. Combining zinc oxide and zinc sulfide nanowires into hybrid structures or dope systems opens up new avenues for enhanced functionalities. This approach leverages the strength of both materials, leading to novel devices with superior performance, such as enhanced photocatalysts, tunable optoelectronics, and advanced biosystem. Related to synthesizing of the materials, chemical vapor deposition, vapor liquid solid, hydrothermal synthesis, and solid methods can be emphasized. Various methods enable the precise control over the morphology dimensions and alignment of the zinc oxide nanowires, crucial for optimizing their functional properties. These approaches leverage different growth mechanisms of achieve desired nanostructure. The synthesis of zinc sulfide nanowires employs a variety of the techniques categorized by primary mechanisms of material growth: chemical, physical, and biological methods. Each approach offers distinct advantage in terms of control, purity, and scalability. For example, chemical methods can serve solution phase reactions like solvothermal and hydrothermal synthesis, offering good control over doping and morphology. And when we look at the physical methods, the vapor phase growth techniques such as PVD and CVD, known for high purity and crystal quality. On the other hand, when we look at the biological methods, the green synthesis using microorganisms or plant extras environmentally friendly and cost-effective products. Again, I'll try to make a table in order to compare production methods by temperature, cost, and crystal quality. High temperature, I should say, high temperature methods like CVD generally yield higher purity crystals, but are more expensive and energy intensive. While low temperature solution-based methods like hydrothermal synthesis are more economical for large-scale production. After definition of my materials and process, now I would like to give you some information about computational material science and engineering. I mean, computational insight, modeling the nanowire properties. Before expensive and time-consuming lab work begins, computational methods allow us to simulate and predict the behavior of nanowires. These powerful tools accelerate the design and discovery of new materials and devices. These simulations guide experimental design and optimize material performance without extensive trial and error. So we use LAMS, large-scale atomic molecular massively parallel simulator, Abacus, it's a finite elemental analysis software, and FDTD, electrodynamics, finite difference time domain methods. In this stage, the density function theory is very important. So demonstrates how bandgap can be precisely tuned via strain and heterostructure design, enable the creation of materials with tailored optical absorption. The other one is Stack-Solver. It simulates electron transport in nanowires, accurately capturing complex short channel effects and optimizing gate configuration for high performance devices. And Charge Solver, it is a physics-based electrical simulation tool for semiconductors device, which self-consistently solves the system of equations describing the electrostatic potential and density of the free carriers. The drift diffusion model is a well-established and robust method that produces accurate results for a wide range of semiconductors devices, semiconductors, devices under common operating condition. Every time scientists make new advances, so mechanical learning integration, in-situ characterization, simulation, high-performance computing, and advanced in parallel computing and GPU acceleration have enabled large and more accurate simulation and so on. Multi-scale modeling, bridging atomic scale simulation with device-level performance, production remains challenging due to the computational resources required and the complexity of the models. And surface effects, accurately modeling the complex surface chemistry and defect states, the dominate nanowire properties require the sophisticated computational approach. And lastly, quantum confinement can be explained as challenges in computational nanowire research. Incorporating quantum confinement effects in computational models, especially for nanowires with diameters below 10 nanometers, demands advanced quantum mechanical methods. Nanowires are very important in our lives, especially healthcare revolution, clean energy future, smart technology. They enable next generation electronics, pushing miniaturization beyond traditional silicon limits for faster, more efficient devices. Their unique piezoelectrics and optical properties are driving innovation in energy harvesting and advanced photonics, from self-powered sensors to ultra-fast mechanical communication. Zinc oxide or zinc sulfide nanowires are crucial components in sustainable technologies such as highly efficient solar cells and cutting-edge environmental sensors, contributing to cleaner, greener future. Related to future applications, nanowires, particularly zinc oxide and zinc sulfide, represent a cornerstone of advanced natural science. Their unique characteristics, coupled with refined synthesis techniques and powerful computational modeling, paved the way for unprecedented innovation across virtually very technological sector. As research continues, these diminutive structures will play an increasingly pivotal role in addressing global changes in energy, health, and information technology, fundamentally reshaping our daily lives. So, the pyramid explains our mentality, industrial application, computational modeling, advanced synthesis to find novel production methods, and lastly, innovations. That is our work as a scientist. Again, application and usage area, solar cells, gas sensor, LEDs, biomedical area, energy storage can be given. Despite significant progress, challenges remain in nanowire research, particularly in large-scale, cost-effective synthesis and precise control over doping and defect engineering. Future research will likely focus on scalable synthesis, defect engineering, heterostructure design, integration with AI, ML works. Actually, we start with my team. And for these reasons, inverse design, moving from the property prediction to the targeted design of nanowires, quantum computing, and heterogeneous integration. At the end of my presentation, the conclusion can be drawn. Zinc oxide and zinc sulfide nanowires are undeniable at the forefront of the nanotechnology, holding vast potential for transformative application. By integrating experimental synthesis with advanced computational simulation, we gain unprecedented control over the material properties, paving the way for tailored solutions. Future advancement in computational methods and scalable production techniques will drive continuous breakthroughs in nanoelectronics, photonics, and energy system. And lastly, together, these remarkable nanowires are set to shape a future defined by sustainable high-performance technologies for decades to come. Thank you for your attention. I want to mention that we are open the beneficial project, joint project. Whenever you want, please call or ask question to improve our research. Thank you very much. If you have question, I'm ready.